Hello everyone and welcome to the NPTEL course on pharmacognosy and phytochemistry. In this week, we are dwelling into world of carbohydrates. In this session, we will discuss two industrially important carbohydrate derivatives, and that is starch and pectin. So starch are compounds which are called as ergastic cell contents, that is they are produced within the plant cell as a result of photosynthesis when your carbon dioxide and water is converted into glucose. Now this glucose gets accumulated and increases the osmotic pressure, and as a result plant kind of converts this glucose into storage granules within the organelles called as amyloplast and then saves them as starch. So starches are nothing but polymerized form of glucose which are stored into plants. So but naturally every plant will have the stored starch, but if you have to commercially extract or commercially utilize starches, they are generally obtained from grains and obtained from tubers which are dug and which contains enormous amount of starch. So this can be your grains such as maize, rice, wheat, or it could be your underground tubers such as potato and tapioca, or also called as cassava. So the second example is pectin. Pectin is a carbohydrate which is present in fruits. This fruits may be your orange peel, apple, sugar beet, guava, mangoes or papaya. When you are consuming this fruit, you get a silky, smooth, slimy texture to it, and this texture is attributed to pectin like compounds. So let's first discuss starch in detail. So starch, as I said, commercially is obtained from grains as well as from tubers. Let's see few examples of starches which are there in commerce. The most abundant one is your maize starch, which is obtained from corn, or botanically we call it as zea maize. So if you see this starch in terms of its appearance, now this is under microscope, the maize starch appears like a polyhedral shape with a central hilum and some cracks or fissures emanating from the hilum. Now what happens here is when your plant is converting the glucose into starch granule, you will see a point of attachment to the amyloplast, and that's where your hilum is. Now gradually over a period of time, the sugar molecules built in and they grow in size. Not only they grow in size, they grow in their numbers also as the plant ages. So plant goes on accumulating them in the amyloplast, and the way in which they are accumulated is responsible for a typical appearance of it. Now this appearance also helps us in diagnosis. So maize starch is characterized by a polyhedral outer border, a inner hilum and some fissures emanating from it, generally with a particle size, or what you can say as average diameter around 5 to 30 micron, with most of the particles falling between 12 to 18 micron range. Now as compared to your maize starch, the second starch is your rice starch. As you can see it from here, it's very tiny in appearance. So in terms of size, they are just 4 to 10 micron, but these are also polyhedral. That means they have sharp angles. Now these are polyhedral but tiny. As compared to maize starch, there is one more difference between maize and rice starch is rice starch are generally found as compound granules. That means they will be found as agglomerates. And in some cases, when you zoom it, you might find some hilum, but in most of the cases, they are too tiny to observe the hilum. The third case, or the third abundant starch, is your wheat starch. Wheat starch comes from wheat, that is your Triticum aestivum, which is also a Graminaceae family member like your rice, and the particles here are not polyhedral, but they are slightly oval. As you can see here, they are ovoid shape and slightly flattened. They are large as compared to the previous two, that is 20 to 50 micron, and the smallest ones, very tiny ones, as you can see the ones interspersed here in between, they are about 5 to 10 micron in size. One of the biggest starch particles you can see in commerce are your potato starch. They grow very big, from 30 to 100 micron in size, and they are slightly elliptical with, you can see here there is a hilum or a dot, which is actually the point of origin or attachment of your starch, and later on you can see some striations. Now this is because what happens is, as the potato tubers grow, the moisture content, the ratio of amylose to amylopectin changes, and that gives a slight difference in the refraction between these two, and that is the result you see a numerous striations, or what we call it as lamellae in this case. So starches are generally made up of polymers of glucose, but depending upon their linkage, you can classify these polymers as amylose and amylopectin. Amylose is actually a linear polymer, whereas amylopectin is a branch polymer. So if I have to give the difference between these two polymers making your starch grain, amylose is the tiny component that is linear, but just comprising 20% of most of the starches, and in some cases it might be even less than 5%. So depends again on the source of the plants, but this is generally the minor component. Now amylopectin is a major component, the branch component, adding up to thousands of sugar molecules, and because it is branched, you can see amylose has what is called as 1,4 linkages or alpha 1,4 linkages between the glucose. Here, apart from 1,4 linkages, you also see here 1,6 linkages between the glucose. So amylopectin has two type of linkages, alpha 1,4 and alpha 1,6, whereas amylose just has your alpha 1,4 linkages. Now saying that amylose is actually stored in the plant in form of coils. So this polymer, this linear polymer is actually coiled, and when you boil your starch, it opens up and hydrates. And amylopectin, you will see, because it is branch, it is little resistant to swelling, and that is also a reason why it is not readily dissolvable or soluble. So you see, in terms of solubility, amylose quickly uncoils and dissolves or hydrates and becomes solubilized in water, whereas amylopectin is considered to be water insoluble. If you see room temperature, they have poor solubility, but as you increase the temperature, their solubility in water increases. Now because of the branching, your amylopectin is hydrolyzed, or which is very resistant to hydrolysis. So if you try to break amylose versus amylopectin, you will see breaking amylose is much easier because it's linear. But if you try to break amylopectin, because it is branched, the enzyme doesn't fit in properly because of the branching, and as a result it kind of stereochemically hinders the hydrolysis, preventing its digestion by acids as well as enzymes. Now one more test what you can do to check amylose and amylopectin is their reaction with iodine. Whereas both of them form charge transfer complexes, with iodine the nature of the reaction is slightly different, the nature of association is slightly different. So amylose forms a complexes which give you a bluish black coloration with a good absorbance between 600 to 620, whereas if you see amylopectin, it is more of a reddish brown colored complex with a UV maxima or a absorbance of about 540 nanometers. Now how do you extract starch? Let's take an example of maize starch, which is much used commercially. So what you need to do is you need to take those grains, especially maize grains, and now you know that those maize grains are hard and stiff. So what is done is they are washed in water. Sometimes they are kept in warm water for 2 to 3 days to allow it to imbibe water so that they swell. Now one problem with that is, if you allow something which is rich in starch to be there in water for 2 to 3 days, it is prone to microbial fermentation, and that is something we do not want. So as a result, industry uses two approaches. One thing they do is they can bubble sulfur dioxide gas through the broth, that is your water containing the corn, and what is done is the slight acidic conditions are maintained, and as a result no microbial fermentation occurs. In some cases within that water itself about 0.2% of sulfurous acid is added to give you similar results. So this will prevent the corns, especially the starch which is present in the corn, from fermenting. Now once the kernels are nicely swollen, they are kind of crushed or milled gently. So when you crush or mill gently, what happens is the outer hull as well as the germs start separating out and the starch separates. Now one phenomenon observed here is you will see most of the germs floating here. So they are tiny and they start floating. These are actually skimmed or collected separately to get what is called as germ oil. Now this germ oil is very much rich in vitamins and is used in cosmetics as well. Now this water or this slurry which is now there containing your starch also dissolves most of the monosaccharides, that is glucose and other sugars which are present. It will dissolve the plant minerals, so that your essential minerals which are present and also the soluble protein. So this slurry is very rich in nutrients, and it is one of the slurry which is used in preparation of antibiotics such as penicillin. This slurry is referred to as corn steep liquor. Now this, coming back to our solution, now we have a corn steep liquor which is going into your fermentation industry. Now this starch is loaded or is stuck in between gluten, and you know gluten is a little proteinaceous matter. So what is done is this gluten is also allowed to hydrate and it will form sticky mass. Now this sticky mass is washed, and as you wash, the gluten remains intact, whereas the starch grains which are entangled within the gluten gets washed. So all these washings will have most of your starch and some amount of small particles of gluten. Now comparing their density, starch is much more denser than gluten. So what is done is you allow it to wash or be washed multiple times till all the starch is removed, and then you allow it to settle. Initially the starch will settle and that will be followed by your gluten. Now industry has also used one trick, is they use a trough which is slightly longer as well as slightly inclined. So what happens is initially on the initial part of the inclined plates your starch will settle, whereas on the last or the end part of the plates is when your gluten precipitates. So you can take the initial plates and get your good quality starches from there. No matter how much you try, this starches will still contain minor traces of other impurities and might require further washings and purification. So once this is done, the starch is dried generally by centrifugation, or you can put it in the tray dryers or flash dryers or moving bed dryers, to which are then subjected to little high temperature but gradual, so that the process of gelatinization does not happen to get your starch. Now other drugs such as potato, which doesn't contain much of the gluten, the process is much simpler. You have to grind it, just separate the cellular debris and pass it through a fine mesh. What is going to happen is through that fine mesh your tiny starch particles will separate down. Just give it a little treatment and you will get your purified starch done. Now once the starches are obtained, industry uses and converts them into much more durable and more useful products, and some of these useful products are your modified starches. So let's see few examples of modified starches. One is oxidized starch. Now these are all edible. So this potato starch is oxidized with sodium hypochlorite, and a slight polar variant is developed, and this polar variant is then used in gels and paste to maintain a good consistency. This E numbers are the food additive numbers you generally see on the food packets. So if you see any of these numbers, you are dealing with starch additives. Another is E1412, which is distarch phosphate. So again, this is made polar by adding phosphate moiety to it, and it gets a unique property, and that it acts as a thickening, viscositive and stabilizing agent, so that your food particles don't sediment very easily and you get a nice ketchup or thick consistency to it. Another derivative is your E1420, which is your starch acetate. Now this is also a stabilizer, but little phobic stabilizer. In this case, it is treated with acetic anhydride to convert it into acetate, and it is also used as stabilizer as well as thickening agent. Now there are some which are called as modified starches, and here one which is abundantly used is E1450, and that is starch sodium octenyl succinate. Now this is done, or this is prepared by reacting the starch with octenyl succinic anhydride, and this has a good utility as an emulsifier and a encapsulating agent. Now this also gives you a little bit of hydrophobicity. Now let's go to a completely hydrophobic starch. This can be done, imagine if you have those hydroxyl groups of glucose and you esterify it with fatty acids, especially you create a modified fatty acid methyl esters and then go to adding it to your starches. What happens is you get a comparatively hydrophobic starch, and these starches have been used to create a good water repellency layer. This has been used to create a kind of waterproof papers or dustings when you want it. The last one is sodium polyacrylate starch. This is when you have polyacrylic acid being used as a cross-linking agent. This is used again in cosmetics as a emulsifying agent, and it has a very unique ability to absorb manifold times its weight of water. So this has been also applied in some cases of baby diapers. So that's many uses of starches. Apart from that, if you see native starch, you have it as a nutritive. You can use it as demulcent, protective and also an absorbent. Now this, if you want to replace your talcum powder with something more subtle or gentle, this has been used for dusting, but you have to take care of the moisture content. Now we know that iodine reacts with starch to give you complex, especially if you remember those amylose coil. So in that cases, when people have suffered from iodine poisoning, the starches have been given so that they can chelate, create a charge transfer complex and encase it in the starch matrix so that the poisoning is not spread. Now this is excellent binding and disintegrating agent used in tablets and also used as diluent when you don't want the drug to absorb too much of moisture. When you want to create a free flowing powder, generally starch is used as a diluent. Now nature of starch different depending upon the drug, the starches vary. We have seen it when we saw the sources, and hence starches can be used as a identifying or a diagnostic agent. It is used to prepare liquid glucose. Once you hydrolyze it, you break it into glucose, it can be converted into dextrose and dextrins with the help of microorganisms, and it is also used in industry for sizing paper and cloth. So these are many but still a limited uses put together of starch. Now let's go to the next polymer, and that is your pectin. Now when you say starch, it was a homopolysaccharide. Pectin is a heteropolysaccharide, and it is there as a heteropolysaccharide containing variable number of sugars. Now the amount of sugars may be in thousands, and if you see the molecular weight, it ranges somewhere between 20,000 to 4 lakh. So this pectin is naturally a component. If you see the higher plants, you will see it in plant walls, especially the gymnosperms, also in pteridophytes, also bryophytes. So primitive plants have it in a scanty ratio, but if you see most of the higher plants, it will be there, and they are abundantly found in fruits. Commercially, pectin is obtained from orange peels and apple pomace. The reason is, if you see the composition, So once the oil and other ingredients and moisture is taken out, you will see citrus contains like very high percentage, almost 30% its dry weight in terms of pectin. Now this pectin you can visualize. So when you take an example of banana or any raw fruit, when the fruits are raw, they are very stiff and they are very hard. The reason is you have pectin in a highly polymerized cross-linked form, and that polymerized cross-linked form is called as protopectin. As the fruit goes on maturing, some of these bonds kind of break up, and then from a highly cross-linked structure you have something which is less cross-linked, and as a result the fruit softens, and that is what we call it or refer it as pectin. But if you see a banana post maturation, so when you call it overripe banana, so what happens in that case is there are enzymes doing this deterioration. So from protopectin they made pectin. Now from pectin they will convert it into pectic acid, that is breakdown products. The pectin is no longer able to hold shape and converted into small units of pectic acid, and as a result your fruit becomes very flaccid and soft. So that is how, or that is the role of pectin. So what exactly is pectin? So if you see pectin, this is made up of linkages. Like I said, it's a heteropolysaccharide, but let's start with something simple. So imagine first a homopolysaccharide of alpha 1,4-galacturonic acid. Galacturonic acid is uronic acid derivative. So your CH2OH gets converted into COH. Now what happens in the process is if we methylate it, you get called what is called as esters. So this uronic acid derivatives may get esterified. So majority, the biggest part of your pectin, say about 65% of your pectin is actually methyl esterified derivative of galacturonic acid. We call it as homogalacturon. Now this is 65%. So what is the remaining percent? Now in some cases, now imagine this polymer going little longer, increasing in domain, and in between the sugars are replaced by rhamnose. Now if it is replaced by rhamnose, what is going to happen is you are getting alternate chain of galacturonic acid plus rhamnouronic acid derivatives. So alternatively, this is what is called as your rhamnogalacturon 1, which is the main part and which consists of another 20 to 35%. So main is a pure homogalacturon, then you have your rhamnogalacturon 1. Now this is not all about it. Now just imagine apart from rhamnose, now there is a branching. Now this branching is done with help of different sugars. You can imagine about 11 different type of sugars, including your xylene, apiose, arabinose and so on. So many of the sugars go on cross-linking and forming other side chains. So now because they are side chains, they are going to be more branched, more cross-linking, and that is what is called as your rhamnogalacturon 2. So this comprises of another 1 to 8%, and a small percent which is intervened by xylose is called as xylogalacturon. So all these 4 portions put together make up your pectin, which is a heteropolysaccharide and is a big bulky polymer. Now this is often found in association with cellulose and hemicellulose along with the proteins and needs to be separated. So let's discuss how do we extract pectin from the plant source. So like I said, commercially it is obtained from orange peel because it has about 30% of its dry weight. So we take this lemon or citrus peels, we boil it because pectin has a good water solubility at higher temperature. We boil it at a little higher temperature close to boiling point, say about 90 degrees Celsius for half an hour. Now during this process, in order to facilitate extraction of pectin, what you can do is you can maintain the pH on a little acidic side. This will promote hydrolysis, promote like little conversion of small molecular weight pectin, and those will be easier to extract post hydrolysis. So you can do that with help of organic acids such as lactic, citric or tartaric acid. So once that is done, still majority of the part remains within the citrus, so you can completely squeeze the peels, remove out how much ever water content you can. So you will get a solution which is little colloidal and turbid. Centrifuge it and you will get your clear solution. Now this clear solution does not only dissolve pectin but also has the ability to dissolve small monosaccharides as well as proteins, and in some cases your starch particles also come along. So what is done is it is subjected to enzyme hydrolysis. We call it as clarification. So this clarification is done by amylose, which deteriorates the starch, and certain proteases which deteriorate the proteins. Now you have a very clear solution containing your pectin, but the enzymes are there. So in order to inactivate the enzymes, the solution is heated one more time so that those proteins get denatured or inactivated. So after inactivating the enzymes, what is done is some pigments also make their way. In order to get rid of the pigments, you give it a good charcoal treatment. So it is decolorized with help of activated charcoal and then passed or filtered. Now this filtrate contains dissolved pectin, and this dissolved pectin, being a carbohydrate, can easily be precipitated by water miscible mid-polar organic solvents such as alcohol. So you can use methanol, ethanol or even acetone. In this solvents, these carbohydrates are insoluble. So the moment you add them to the water, you are going to have a precipitate of pectin coming out. Now this is slimy and mucilaginous. So to remove the water which is adhering to it, it's still washed with more water soluble solvents and then dried in vacuum to get rid of the moisture. Once that is done, it is pulverized and stored in a airtight containers. So pectin is yellowish to white powder, it's odorless, mucilaginous. Now like we discussed previously, if you remember, this methylation. Now depending upon how much methylation has happened, you can actually divide your polymers into high methoxypectin and low methoxypectin. So what is the difference? High methoxypectin contains more than 50% degree of esterification. That means in terms of your uronic acid, most of the more than 50% of the residues have been methoxylated, whereas low methoxypectin, less than 50% have been methoxylated. What is the difference that the degree of methoxylation or degree of esterification creates? High methoxyprotein are more water soluble as compared to low methoxyprotein, and as a result they vary in their gel formation properties. If you deal with high methoxypectin, they require, or for their gelation they will require a combination of acidic pH and sugar. Only when these two are given they form gels, otherwise they will not gel properly. Whereas when you are dealing with low methoxypectin, in that case you will require metal ions such as calcium, and pH is, or maintaining acidic pH is not necessary. So here the gelation can happen over a wide range of pH. Now comparing the gel strength, high methoxypectin gives you a stronger gel. Imagine you are consuming your gummies. So you get something like that, whereas low methoxypectin is something like a very soft, imagine the glazings of the cakes or pastries. So they form very soft gels with a nice soft, smooth, pliable consistency, but they are more elastic, whereas the high methoxypectins give more friable gels. Now here the applications of high methoxypectin is jams, jellies, generally because they require high sugars for their gelation and they give you a very firm gel. Whereas in this, if you see in your fruit fillings, the soft glazings or toppings, those come mostly from the low methoxypectin derivatives. So uses, both high methoxy and low methoxy have been used in food, industrial as well as pharmaceutical sectors. In food they find applications as thickening agents, viscositives, pH stabilizing agents for especially dairy products and low calorie products. because of their nice carbohydrate and alternating soft nature, they can also been used as a very good emulsifiers. Not only that, they also been used in design of drug delivery systems, so especially your gastrointestinal one. Now they are water soluble fibers, they are water soluble carbohydrates which create viscous solution. So they decrease the absorption of nutrients like your carbohydrates, they decrease the absorption of cholesterols or lipids, and they have been also proved beneficial in cancer treatment because they fall into the category of prebiotics. So they can also be used as safe for consumption edible films, coatings, foams, and even paper substitutes. Now when you see bioengineering, pectin has found its application especially in tissue engineering, wound healing, gene delivery, and also in novel drug delivery system. Not only that, pectin is derivatized. You can have different degree of esterification. Some of them add functionalization like amines and other functional groups are added, and newer approaches and applications of such derivatives have been developed. So here are few references if you wish to know more about starch and pectins, and thank you everyone for your patient listening.